Today we're talking about gearing solutions, and I'm so pleased to introduce Mark Perkins, a senior design engineer at Winsmith, to share his knowledge. For the benefit of our audiences, I'm going to ask very specific questions to help bring out the best of this conversation and make it really useful to them. So, as automation and electrification accelerates, how are expectations around backlash, efficiency, noise, and durability changing? So really my question here is, where do you see design engineers most often needing to rethink legacy assumptions?
For backlash, in the distant past, backlash was something that was necessary in the manufacturing process to accommodate different nonconformances in the gears or less precision that we had in the past. As machinery has improved and design has improved, those backlash specifications have been easier to meet as customers have needed tighter and tighter backlash in their gearboxes. Winsmith's developed different products to meet those customer expectations, while the specifications for the standard product lines have improved, where more accuracy and tighter backlash specification is required. There are different technologies that we can employ to meet those specifications. So it's not, as in the past, a required feature. It's more easily controlled now, and less backlash is required to accommodate those manufacturing tolerances. For efficiency, we've seen, especially with worm gearing, great improvements in efficiency in the past few decades. Improvements in lubricant and material selection, accuracy of the gearing, all those things have combined to create a much more efficient product. The same goes for helical inline gearing, bevel gearing. Those other products have gotten better too, with improvements in lubricant and accuracy.
Looking through your website, looking at aluminum, for example, aluminum housing in gearboxes, talk a little bit, again, just at a high level about different types of materials that are being used now.
Sure. Housing materials don't have as much of an effect on the efficiency of the gearbox. For structural integrity, they do a good job. Aluminum is good at getting heat out of the gearbox a little faster. For where you need the gearbox to be a structural component in the system, cast iron does a good job. If you need more strength than that, you can switch to ductile iron or even a steel housing. So for housing material, that's what you would normally go with. For efficiency, you're looking at the material for the gears for the most part. So C917 bronze is a pretty standard industry material to use for worm gearing. That offers a good balance of strength and coefficient of friction to help efficiency go higher. The lubricant is the big driver for the most part. PAG lubricants have been a game changer for the worm gearing industry. Synthetic lubricants all across the board for all the other product lines as well. Usually a PAO with your planetary and your helical bevel, your helical inline, those products. A big improvement from the mineral oils that were used in the past.
Okay, so let's talk about integration. So in designs these days, where do integration issues most commonly arise between the motor, gearbox, and control systems? So, and also how can earlier collaboration across disciplines improve overall machine performance? I just want to say here, in asking that question, I hear so much about that the design engineer needing to be the need for them to be part of the process earlier on, or at least they need to be able to have a conversation about where it's going in the future as well. So talk to me about integration.
Yeah, it's a common problem that we'll see with applications with some customers that aren't familiar with using gearboxes or considering the way that they need to be integrated into the system. Efficiency gets overlooked sometimes. So 1 horsepower in is not always 1 horsepower out, especially with worm gearing. And if you don't consider that as you design your system, if you've got to size up because you don't get the output torque you needed with 1 horsepower in, if you're not getting a horsepower out and you needed to have that, you can't always size the motor up without sizing the gearbox up. If you don't leave enough space for that, you're painted into a corner and you're left with some tough calls that you need to make. Um, Interface two for the mechanical part of it, making sure that you're paying attention to how that torque is getting into and out of the gearbox is important. If it's a motorized unit that has the motor directly mounted to the gearbox, that feature needs to be rigidly and accurately positioned to avoid noise issues. On the output end of the gearbox, it's important to get the alignment correct because again, you can look at noise issues or inconsistent torque transmission. If you're driving a sheave, a pulley, a chain drive, something like that, the output or the overhung load on that output shaft is important to consider too. We've had customers that have correctly sized a gearbox for the torque they need, for the horsepower they need, but we've seen them not consider the force on the gearbox and the shaft. And that can lead to those overhung load issues where the shaft might not have the integrity you need. If it's pulling in the wrong direction, the housing might not even have the integrity you need as part of the system to do its job.
You talk about alignment. So, how should engineers think about thermal limits, duty cycles, and service factors when they're selecting their gear solutions? And specifically, in highly dynamic or continuously operating systems. So, and the question here really is, what are the consequences of getting it wrong if you don't align thermal limits, duty cycles, service factors? Expand on that.
Most catalogs for standard products, worm gearing and non-worm gearing, your helical bevel, your helical inline, those kind of products, will typically provide some guideline about what the thermal limitation of the gearbox is. And if you ignore that part of the rating, you run the risk of running at elevated temperatures. So you have oil running at too high a temperature will degrade too quickly. It will cause accelerated wear because as that temperature increases in the oil, its viscosity decreases. You'll have an accelerated wear condition on the gears. The bearings don't like that all that much either, but the seals will also see an accelerated wear. If you haven't selected a seal material that will handle the temperatures you're expecting to see, you'll see embrittlement of that. Typically, rotary lip seal used in many gearbox industrial applications, you'll see that material embrittle and fail, and you'll see leaking out of that seal to shaft interface. And if your oil gets out of the gearbox, you're only going to accelerate those thermal conditions, and you'll see failure much more quickly.
And also from a system level perspective, what design choices have the biggest impact on noise and vibration?
That I usually work with a colleague for the higher level noise and vibration things. Again, alignment's important. We've had customers return units for complaints of noise or vibration, and we'll inspect all the components on the gearbox and find nothing and go back through their system build with them and find that it can be as simple as just not aligning the output shaft from the gearbox with their driven equipment. If there's misalignment there, the coupling is going to make noise. The same goes for the motor. If the way you're driving the gearbox is not providing good alignment between all those connecting components, you'll experience noise and vibration there.
I want you to talk about uptime now and talk about how gear design, condition monitoring, and maintenance strategies work together to improve long-term reliability. This has been an ongoing conversation from my days of covering MRO. So now being on machine design, I'm very curious to hear a perspective from the design engineer how you approach what your approach is.
Sure. The condition monitoring that's offered now is very useful and helpful for customers, especially where it's a larger gearbox or more expensive gearbox, and it's integral to the system that you're running, and the downtime will be very expensive. Even if it's an inexpensive gearbox, you can't afford to have the gearbox fail and go down. So if you're monitoring temperature and vibration and watching for changes in that over time, you can predict where the failure is going to happen. Especially with smaller elevations in temperature that occur over as a pattern over time, you might get an early indication that you need to do that oil change, maybe sooner than the manufacturer recommended. All we can do as a manufacturer is suggest what the best practice might be for that lubricant change, but your application conditions are always going to dictate what that change frequency needs to be. So monitoring the gearbox, if it's just temperature and vibration, that is a good start. If it's a really critical application with unique environmental application conditions, taking samples of the lubricant and getting it analyzed over time and developing a trend might help you determine how often that frequency needs to be for the lubricant exchange.
Mark, that's fantastic. I just want to say thank you so much for your insights today. It's been a pleasure to learn from you.
I was happy to be here.